Hello. This is a presentation of a paper interpreting intermediate convolutional layers in unsupervised acoustic word classification by Gasper Begush and Alan Zhou. So understanding how deep neural networks learn representation is internally has long been desired in deep learning literature, but most of the interpretability work focuses either on the visual domain or on text-based language models. In this paper, we proposed a new technique to interpret and visualize intermediate layers of deep convolutional layers trained on raw speech. And we introduced statistical modeling into the paradigm. More specifically, we introduced nonlinear generalized additive mixed models, or GAMs, that allow us to infer underlying distributions for each word in intermediate convolutional layers. And we can analyze both absolute values of encoding as well as shapes of encoding for individual words at each convolutional layer. And again, because this is statistical modeling, we can do hypothesis testing on the outputs of our technique. So the main proposal is averaging over individual feature maps in each convolutional layer after the leaky railway activation in a classifying network yields highly interpretable time series data that summarizes which linguistic properties are encoded at which layer, at which intermediate convolutional layer. We propose a similar technique for the synthesis aspect of GANs, where we focus on the generator, but here we focus on the classifier network. So how does our model look like? We take the ciwGAN proposal from Begush 2021, which is an InfoGAN extension of waveGAN, a GAN architecture for modeling audio data. And so the proposal has three deep convolutional networks. One is the generator that takes some codes, either one-hot encoding or binary codes, and Z variables, which are uniformly distributed variables, and through a series of convolutional layers generates audio data, in our case, speech. This gets fed to the discriminator along with real training data from TIMIT, and the discriminator needs to figure out what is real and what is generated through the Wasserstein distance. And then we have the Q network, in our case, a separate network, unlike in most InfoGAN proposals. This is a separate network here that takes raw generated audio, not the training data, but generated audio, and needs to estimate or figure out what unique code did the generator use when it was producing a given audio output, okay? So you train the generator such that it maximizes the success rate of the network. In other words, we're forcing the generator to produce informative data. And we have the Q network then that takes audio and classifies it, okay, in a fully unsupervised way. Now, the lexical learning needs to self-emerge in fully unsupervised way in this particular architecture, right? The Q network takes audio and needs to classify it. And the generator needs to take some code and some information, some code, and encode and transform it into data. Now, given speech, the most informative way to encode unique codes into audio is to use lexical item and pair each unique code with each unique lexical item. So lexical learning self-emerges in this architecture. Now, what do we have here? We have a generator, which is the synthesis or production part of this model. But then now we have also the Q network, which represents the perception part, if you want. So, or a lexical classifier part, where the network takes raw audio and classifies it according to lexical data in a fully unsupervised way. And if we look at the architecture, actually, the Q network is twice removed from training data. So the generator never directly accesses training data, but the Q network only accesses the generated output. So it never really sees the real training data. Now, what we do in this paper is we take, after training, we take the Q network and feed it real TIMIT data from the test data distribution, right? So we split data into training and test. We train the whole architecture, then we isolate the Q network and feed it raw TIMIT data, test data, and see how it transforms unobserved TIMIT data into classification through a series of convolutional layers. So if we zoom into the Q network and its structure, we have about 16,000 data points coming in. That is the input layer, which is about 1 second of audio sampled at 16 kilohertz. And through 5 convolutional layers, it results in 1 hot encoding at the final layer, for example, with 8 levels. Why 8 levels? Because we first trained it on a smaller data set, namely 8 lexical items from TIMIT: ask, dark, greasy, oily, rag, wash, water, and year. We split the data, 80% is training, 20% is test. About 1,000 data points is test data. And we do averaging over all individual feature maps for each convolutional layer, as was mentioned before, to get this really interesting interpretable time series data, where we can see how individual raw audio input gets transformed through a series of convolutional layers into the final layer, which is the classification layer that decides between the 8 levels, the 8 possible levels. And you see that, you know, at the more shallow layers, you have a lot of information encoded, right? You have vocalic, periodic vibration. We have a frication noise of an S in a case like ICASSP. So these are individual words, individual waveforms visualized throughout the convolutional layers using our proposed technique. And you can see, for example, how bursts are encoded and how things get increasingly more abstract. But this is at the individual word level. What we can do in addition to that is actually we can visualize all 1,000 words or instances of test data, and we see that patterns emerge. We see that words like a word like ask has this type of shape at the 5th convolutional layer, for example, at the final layer where things are most abstract. A word like oily has a different shape. A word like greasy has a different shape. So in order to quantify these shapes more precisely, we use nonlinear regression techniques, and more precisely generalized additive mixed models that estimate both absolute values of, say, individual words based on this 1,000 test data, as well as their shapes, right? So now we can basically do inferential statistic tests on individual values of words as well as their shapes. And these are the smooths based on the nonlinear regression. And we see that words have distinct shapes at the 5th convolution layer, and that is likely how the network encodes identity of these individual words in this fully unsupervised manner trained from raw speech. With this technique, we can not only test encoding at the word level, but we can go deeper and test how individual phone contrasts are encoded. And again, we can test both shape encoding, in other words, how some linguistically meaningful unit is encoded with shapes at individual convolutional layers, but also at how they're encoded within absolute values at each individual convolutional layer. So to test how phones are encoded, we can annotate the difference between, for example, 2 sounds, S and sh, 2 fricatives in English, in words like ask and wash. And we see that at the 1st convolutional layer, the difference between S and Sh is encoded with shape, right? So the smooths here differ primarily in shapes, as you can see. But then as the encoding gets transformed into the final layer, the encoding changes from shape encoding into absolute value encoding. For example, at the 4th convolutional layer, we see the shapes of S and Sh in ask and wash. The fricative part of ask and wash are the same. They do not differ significantly among each other, but the values, the absolute values, differ significantly, right? So we see how the shape encoding gets transformed throughout convolutional layers into this absolute value encoding for each phone difference. And the one nice thing about using nonlinear regression in other words, generalized additive mixed models, is that we get estimates and we can do hypothesis testing on differences between words, right? So we can say in absolute values, so parametric coefficients, as the word for ask differs in absolute values from greasy and oily and year significantly, but not from other words. And in terms of shapes, of smooth shapes, as differs from all other words in the experiment. What we also do in the paper is see how this scales up to larger models. We train, we do visualization and interpretation of intermediate convolution layers on a FIWGAN model, on a pre-trained one that differs from the model I just talked about in two things. One is the encoding here is not one hot encoding, but binary encoding. So we have codes, and the model is trained on the entire TIMIT. We find the exact same thing or very similar conclusions. So we can visualize and analyze shapes of individual words, even in these larger models. And what is also important is we can identify at exactly which samples do different words differ, because we are fitting the data to a nonlinear generalized additive mixed models. And so they estimate also the different smooth between different word pairs. For example, ask and greasy, these two word pairs, see they differ in this part of samples, in these samples, and in these samples, because that's where the 95 confidence intervals do not include 0. Okay, so to conclude, we propose a technique to interpret and visualize intermediate convolutional layers when network learns to classify words from unlabeled data in a fully unsupervised manner without ever having access to the actual training data. And this is going to be increasingly important because speech technology is moving towards unsupervised learning, and understanding how contrast and words get encoded in these models is going to be increasingly important. We introduced inferential statistics to the paradigm to infer underlying distributions of word or phone representations. And this allows inferential statistical tests of both value encoding and shape encoding at different convolutional layers. Any acoustic contrast can be tested and compared with this proposed technique. And actually, the technique has the potential to serve as diagnostic for detecting layers at which speech contrasts, such as word differences or phoneme differences, fail to get encoded. So we can use this technique to see, okay, at this layer, my encoding fails, or I switch from value encoding to shape encoding and so on, to give us cues as to how to repair that failed encoding, for example, increase sample size or increase the number of layers and so on. So with this and some references, I thank you for your attention, and feel free to get in contact with us either through email or our lab's Twitter account. Thank you very much.